So I presented to slide pack in actually of yesterday. So when I was handing in the abstract of the title, I thought toric, especially toric varieties, would be slightly more vivid, and in particular also include the combinatorial side of this conference. But the examples we are considering the general setup, they're really expensive. So that's the value of it. And it also influences for this, as we saw in the beginning of today. So I thought it would be good idea to emphasize a little bit in the study. So I'm talking about going through the outline on one page, and then we would start outlining and we're talking about and the general setup is some consider at the beginning projected variety over C, although base field doesn't really matter actually. I mean, we could work with any other base close to A, and I want to freely quote sometimes they use the survey. Group of different sheets. Yeah, B is derived from the sheet. We saw that actually yesterday in class. So the derived category is an interesting invariant. So sometimes it tells you everything about the underlying geometry. Sometimes it doesn't. But I'm not a derived category person, so I won't talk too much about that. But I will give you some essential definitions in order to put that in context. The paper, especially in the one with class, I mean, it's basically everything is combinatorial. So let's take that as a definition. It's not a really bad profile. So what a line bundle or a vertical sheet is like that is doesn't need explanation, but let me recall what the exceptions are. Object from the derived category, and I call that exceptional. Following holds, so consider the arrows in the derived category of P to P by a number N. So if you wish, you can also think of it in terms of compounder. That is supposed to be the ground with C. 0 and back to finish. So that is an exceptional object, and well, give you one example. So that is the case of a line bundle. So what does this condition mean? So here I have a derived category. And let me call that K. So that would be the X function. The X function of L over L. And then you bring that to the other side. And what you get is essentially the homology of L minus 1 tensor L. That is L X. So the line bundle will be exceptional if the structure is not exceptional. That our and the finite holds. So it will be exceptional. And therefore any line bundle. So so this provides us with the yeah. And you want yeah, it's the shift. So I'm just applying
It's zero.
here.
It's A.
It should be K. Yeah, sorry. Thank you. Yeah. Thank you. Yeah, it should be K. Right. So X is exceptional, and therefore any line bundle is exception. So that provides us with a huge supply of exception objects. And out of these exception objects, I can now form exceptional sequences. So what is an exceptional sequence? So you take a sequence of exceptional objects. And you see that that is an exceptional sequence. Transform and abbreviate by ES. So the following condition holds. So again, you look at the derived category, and condition you want is in essence that there are no vector morphisms, so whenever I consider K and Z, semi-autonomous system in the T is it's quite natural. Let us consider both relatively. We have already seen that line bundles are exceptional. What does it mean for us? So, well, again, I have a look at the defining condition. And while doing essentially the same computation as I did on that I need that the case homology of X Lj minus 1 Li. This is the criterion for relatively handy because what does it say? Basically, says that if I switch now to additive notation, then the difference of these two line bundles in the Picard group belongs to what we call so these are the line bundles. Homology. No formal or exceptionally smaller than is 0, that's not an immaculate form. That's all. Yeah, for I smaller than J. Oh, that is yeah, so maybe I should have put that. Yeah, okay, I mentioned it here. So I needs to be strictly smaller than J, otherwise. Um, yeah, by definition. I mean, just it's an exceptional object. I mean, you need to ensure that your object is exceptional. And that is obviously something which one tends to forget. I mean, if I have a general sequence of objects, I need to require every single object to be exceptional. Now, line bundles are very often exceptional. You're dealing only with the line bundle. Yeah, so with the immaculate locus, maybe just one further remark. That is actually highlighting what I wanted to say. It's like a lot of the reasons to be very fast to write it this way. So what we are doing is draw the let's say the immaculate locus, but it's not. We rather want it to have this. So if J is bigger than the first place, and Y in the first paper with Klaus, we considered the negative method. So here, these are the line bundles. Easier to deal with that negative method. Yeah, the entire form. Oh. Locus, and that can be actually effectively to quite for detecting that could be so that was what they are calling it. For example, now the concrete example, a very famous one. Concrete example, which goes back to Bayes, and I was actually told that that was just a member or a written seminar work telling English. Yeah. So came up with the following sequence on projected space. So maybe start with the effective yeah. This is the classical result. If you have a non-negative degree, then you can't have you have global sections. And a negative degree, you don't have global sections, but there's a range where you're supposed to have topology in the spot. So those alignments which are really immaculate are better the immaculate locus. As a consequence, you can see the following sequence L1. You start, say, give yourself some integer, and then you have this is an exception. It's actually maximum exception. As it would be the less exciting, but you can see very quickly. But maybe we check just and 1 minus and 2. Yeah, like the difference in K. It also shows that I tried to extend that beyond K plus, and then I wanted to. So far as I can summarize every maximum functional feature. Now that itself wouldn't be that interesting, but as a further very desirable property, namely it generates the derived category of Tn. Write that like this. So that basically means that the smallest full triangulated subcategory of the derived category containing the exceptional one line is already the implied. So this way, the exceptional generates the derived category, and we can have full. So if I have an exception sequence, the derived category is an exception sequence. Really apologizing to the French speaking community that we know unintended and for full. Okay, and these two
on the maximum.
Yeah, they do. I will just come back. Okay, it depends on what you call maximum. I mean, if you say maximum in the sense that they are not extendable, can have can't extend beyond the further point, but you can construct other exceptions because it's a longer. Yeah, for instance, I mean, probably the simplest examples. I mean, I have more complicated examples. I guess, but there's a bound. There's a bound to this end. The regular category. I come to this in a moment. So maybe just before I.
Was there some implication between the then maximum?
Yeah, that's precisely the point. When I'm just maybe, as I said, I'm not really like not really a lot at all about some ideas why fully exceptional treatments is why they are important. Well, basically, they give rise to what is called a semi-orthogonal orthogonal decomposition. So there's a formal definition that basically means that you break up the derived category into smaller pieces, which hopefully can be. This way, you can see a think of a semi-orthogonal decomposition. First structural approach to understand the derived category. In particular, so this is a more general concept of sequence, but every has derived such a decomposition. And in particular, if you have even something which is called, now I have always a doubt, it's strong, sometimes called strong exceptional or strongly exceptional. But I'm not a native speaker, then I would tend to call that strongly exceptional. But I have seen both variants in the literature. So if in addition, that means in addition, a j, a I of k is 0, and this time for all a j, so it doesn't require the order anymore, and for all k bigger than 0. So if I have that, then I call that a strongly exceptional. These strongly exceptional they give rise for the Chiltern sheet. And these guys are much sought after in representation theory, because once you have that, you can say that your derived category is equivalent to derived category modules over the endomorphism ring. Okay, as I said, I'm not an expert, but that's also a motivation why people are looking for these fully exception sequences. And then third point, maybe Max here know much more about it in some resolution is I think also applications in this quantum commodity business. So just to tell you why it's desirable to be able to deal with fully exception. Now to the question of maximality, and that is somehow the very heart of this talk. Once you have a test, as I said already, I mean, this n is always smaller or equal to n. If I have equality, so remember that was the rank of the category. And if I have equality, then I'm speaking of a maximal exception sequence. If on top, this maximal, well, if I have a test for the moment, I don't know whether or not it's maximal, but it is because it basically, if you construct the Broglie group of the triangulated category given by derived category, so that's isomorphic to k naught of x. And then under this isomorphism, it turns out that if I have a full exception sequence, this will be just a lattice given by the classes of the EI in the case. So and therefore, and if I have a S, then it's a mess. So n equals small n equals capital N. So the question is now, does math imply text? So that is actually an interesting question. So to answer the question straight away, I mean, the converse doesn't hold, and that is due to so-called canon. So a converse So these are somehow pieces. Well, I was same. Sorry. Yeah, it's the other way. Yeah, yeah, yeah. Yeah, thank you. So that is to be something categories. These are some categories checked by looking at things. Also, for a long time, not so clear these categories they exist, but they do. And afterwards, that's not. And I see him address in 2014, state of the art, and then that was somehow embracing the best possible case, which was not structured by counter examples that were assumed or exist. The examples are so far of what happened to there were no fully. Then the formula should so that now turned out to be, well, one can probably say that's wrong by now. I mean, there's a reason. Another example. By Johannes Krah, who constructed who were investigating exceptional sequences of the Reinbach generation surface, and he was actually exhibiting the one which has a fully exceptional sequence, but who has also maximum exceptional. But it's a relatively whole paper, so which measures on any hope that that could be true. Nevertheless, the question is valid. Which geometries can we actually less that I have less. These reasons mean one starts to investigate that question via line bundles because they're relatively accessible. I mean, it would be very desirable to have also more complicated. For example, examples. So they must talk. So that is a very active area of research, but it's also very complicated. So I don't want to do anything fancy from here. So from now on, only. So if I say S mess or S, I always have line bundles. So even there, it's some subtleties. For instance, the Efimov, in a very beautiful paper, that there are toric varieties which do not admit any even any maximal exception. You don't even reach the bound theoretically possible by the case theory. So so then jumping into that problem, I mean, you need to somehow to ensure that you are on a geometry which cases for testing. And that brings me to the third one, namely the projective eyes for vector bundle. versatile too.
Are these non-examples, before non-examples, are they projected?
Yeah, projected, final. They're really quite nice, yeah. Because actually, when people were thinking that somehow you could on a toric. Yeah, I mean, okay, I should maybe to put that into context. I mean, here it's now, this is something which is important. So I could say on the good side, look, as so of general objects, so now contradicting what from now on beyond this line, I will only consider masses of general time can have complexes of sheet. They exist in toric varieties. On toric varieties, so that is due to Kalamata. That's a very nice result. If there's one drawback that was very implicit, the uses toric Mori theory and a lot of stuff you don't really understand it. It's an abstract existence argument. So in toric geometry, you would prefer to get your hands on the objects. But at least toric geometry is a good place to start. Consider this question. Test doesn't need more tests. If you're interested in for line model, as I said, you need to be able to pay attention. So this as a kind of general introduction now to the point. Yeah. So what we were doing, so we were considering or we're investigating and answering this question and the property side for the following three things. That is the joint work with Alpha, which tells Alpha and Andreas Hohenegger. So so we have mass and price test for the following following things. With the setup is this. So the projected spaces is very simple, but it worked remarkably well. So we don't want to be too far away, but still want a little bit more complicated. So that's where the projected projectivized vector bundles come into play. So I consider X, the total space of a projectivized tangent bundle. It won't be of, as I don't go into any explicit computations, it won't be it won't matter much, but just as a slight caveat. But I think we had yesterday the other convention. So for me, it will be you see what I'm doing. We had a long discussion, and I can tell you, I was really fed up at the end to change over and over the convention. So we finally stick to this one. For the good or the worst of it, I don't know. That's just as a small caveat. It has the advantage though that, for instance, only of Eisenbach's book in the second course in geometry. That's good. Wait, so that is just. I don't want to create any penalties. And I will consider these bundles for the protection over the protection. So that's pretty simple, but it encapsulates already a rather rich class of several geometries. Mainly we have, well, maybe I should start pointing out existence. Why do we do that? Well, we have existence of pets in a rather natural way, resolved by all of which applies in greater generality, tells us that if we take if we start by the usual it in sequence. And then every projected on every projectilized vector bundle we have a button 52. So here we make some choices. I mean, we get just what outline, but we change that a little bit. That is, we just assume we have a relative, and then that is the set on the base. And base I call it. Here the rank will be half of 1. Vector bundle, the base will be n, and then that's correct. And I get, well, basically, what I'm doing is I'm tensoring, so with, here with the trivial bundle, and then so that goes until n0. You probably got the logic already. And then I start the tensor with O H and so on until I reach okay, I hope I'm not mistaken. I think reach 8, 10 tensor O O L or H. Okay, that gives us we refer to this as a trivial test or of fully exceptional sequence of this type as being trivial or all of time. That is already good news. So we are not speaking about the empty set. And then well then there are, I mean that is still far too general in order to, at least for us, to be tractable. So achieve not arbitrary vector bundles. I mean among this among the toric vector bundles complicated, so we are doing very simple things. So the first case to consider is where your vector bundle is split. First case where we have actually two subcases. It really is the direct sum of R plus 1 copies structure sheet, and in this case will be just the product space R times En. Take a direct sum of models. These two cases are by a result of Schmidt from the 80s. They're basically three toric varieties of rank 2. I mean that so that is toric. I mean maybe slightly less than this, but it's toric, and it's based on this probably less every, well that's difficult, but needs every rank 2 smooth solid variety comes from the technique condition. How we took Well, explicit computations we did it for Q2, although in this case worked a little bit less well. I will explain that. For technical reasons, there's a little twist. You might wonder why this is just because it indicates rather that we took a slightly different type of context. That is basically we want to use the hyperplane section to be a generator of the left cone. So that's just the truth of the word slight. It's really special. In this case, X got well, a variety of flags. You can, in principle, do that also. Very complete picture, and it's very nice to write up. If I have time, I will just indicate here it works slightly less well, and there are a couple of every next one sequences that we can check for performance. In principle, it's doable, but it's but at least the example has the ability to say that it's not something they expect. For the 90s, okay, maybe I should do, yeah, maybe some are in order before I will just demonstrate a little bit how we proceed. I mean, the idea is this. The idea consists in showing that any map arises from a trivial test, which I gave over there, and a finite number of steps, the finite number of steps, and each step which modifies my original maximal sequence starting from astronomers. So, essentially, yeah, I have here, I gave you here one concrete test, but there is actually some continuity in use around case. There's some flexibility in what we can show is that starting with one of these different types of tests, we can essentially capture the entire world of maximum sequence. I do so except I modify my trivial sequence and I render the trivial sequence slightly less real, but I do so by preserving fullness, and in this way I capture any mass, and in this as a result mass implies test. So that works well in one-to-one. Maybe that's even a trivial fact, and maybe it is actually. I wouldn't exclude that, but just to put that result in context, ask, for instance, well, starting with the product of two projective spaces, what can be an arbitrary so the case P1 times P1 times P1, which you could try to handle along these lines. This requires actually, we don't have a theoretical argument. I mean, powering 3, but it's still not really that powerful, you think. So mass implies test correct. And it requires the aid of the computer. This is a paper by Klaus and his son doing the computer work. So you can cut down they cut down the number of methods in a precise way, but still it's that smashes maybe any hope there to have a very easy generalization. And so maybe that, at the end of the day, we have maybe to stick to these some results, but it indicates that it's maybe not completely straightforward. I mean, if it was, I would be happy to especially in this case, not so library.
Is the immaculate locus counting for P1, P1?
Yeah, it's known. It's basically not very remarkably bad at drawing for a geometer, but looks like this. It's actually very simple. But I should. That's a good question. I should maybe mention here. One of the also that is the immaculate locus means. So here in guitar, where you see they are all the fans are so-called splitting fans, and in that case, I mean, there's a very easily developed by Klaus and some of his collaborators, which is Tesla and Vince. We have a very neat picture how we can use the immaculate locus. It works very well for splitting fans in general, and also in guitar rank 3. There's some hope that we can handle this case or such cases because we know the immaculate locus very well. That is actually a PhD project of my students. I mean, to have a closer look at the PK rank 3 case because clearly we have a new idea. I mean, the basics are there. And how you make a run is a different question. So, maybe I should do a concrete example. A very simple but nevertheless a constructive one. We take P1 plus P1. So, one of the immaculate locus, and I really like that board because the discrete question is very nice. So this is the origin. I have which because I have chosen another plane section, always have a natural identification. There are two letters, and here we have an immaculate locus, or the immaculate locus of identification. And again, I should stress it's actually a negative immaculate locus. And so if you just proceed by brute force, I mean, you will see that we have these 4 families. So we have basically the holotype sequences, modular an overall shift. You know, I'm free to apply an overall shift, so I can always without loss in generality that I'm starting at the origin. So I have this. I have 2 subsequent points, so that is basically the valence sequence, or one valence sequence, one. And then I have a second pair which I can freely move around. So these are the previous sequences. These are the previous sequences, and we have this one. Maybe I should. There's kind of fault somewhere. Somewhere here. And we can have this one. So we have a 1 point here, 1 point here. And again, we have a pair here, which we can just freely move along this line. Now, you might wonder, I was speaking about exception sequences, and that's what we need to install in order to speak about the sequence. Now, it turns out that is very important. One of the tails, for instance, we can always logically or lexicographically order the sequence. So these ones I can logically order. There are that is beautiful. Split everything around by 90 degrees with the two other families. So there's obviously a symmetry in here. So I only give these two. And they basically display already all relevant features with further insight. First of all, we see that that their maximum they have 4 points. We can also see by an argument which also runs in varieties and varieties. We can consider the following map. Maybe we go from Z2 to a lattice. So the Z2 over we take well basically you quotient out 0 0 2. So if we are in the origin here, take just this fundamental domain, select everything in it. Turns out it's very simple. That's just because of the immaculate locus. That if you restrict this phi to an exceptional sequence, this is expected. So we have over here four possible spots for the image command. We immediately deduce from that an exception sequence can have at most 4 elements. As we know already, this is full, so we get exception sequences. Fullness requires 4 elements. You get also that fact. It also tells you something that this particular shape is not an accident, because if you project that down, somehow here in this case, if you project down, you land here. So this must match up here with this point. I mean here, so they are already neighboring. Otherwise, you project down, it must neighbor here in this fundamental, neighbor in the fundamental domain. And another feature that is very important, which also fails here in this case, is we have a spatial bound. There's an a priori bound, which we can prove that either your exceptional sequence has a constraint height, or it has a constraint width. It's impossible for the sequence to spread out in a kind of uniform way. As you can see here it says constraint height. If you flip that around, you have constraint width, and that is which together in conjunction with this map makes work a kind of classification. So at least it gives you a classification of the maximum exceptional sequences, so we get a good grip on them. Now the question is, how can we prove fullness? Then there's a highbrow argument, which consists in appealing to the category, to the theory of exceptional sequence derived categories and so on. And there's a well-known operation which is called a mutation. And it turns out that, for instance, the vertical real, and if I start with the arbitrary order, sequence, and after mutation is something which preserves fullness, it can in general be a very awful operation. So turn line bubbles into arbitrary complexes. And in our situation, it turns out to be well. And using this mutation business, we are basically done. Because and moment. But there's also a second possibility. You don't want to adhere to that general possibility, and that is to start what we call a combinatorial game, which again here in this case is rather easy. But it's quite interesting. Let's try to play this game. I think like here, this here we don't get very far, but in general it's more complicated. So let's take for instance here this sequence. That would be one maximum acceptable sequence. So how do I prove fullness? Here, I need also to appeal to internal fact that the derived category is actually, based on the assumptions, it's actually generated by the department. What this means is that somehow I need to ensure that I can generate every point in the net. What does it mean to generate? So if you unravel the definitions of the derived categories, so you need to appeal to exact sequences. I mean, here we can somehow draw on Bailenson's argument, which is based on this the Bailenson exact sequence. It says here in the case of P1 or more generally Pn, if I have a sequence of here, if I'm on P2, say, if I have a sequence of 3 consecutive points, this generates the entire derived category, and we can translate it in such a way that we say, okay, if I have 3 consecutive points, I can in particular generate the entire line, which is for Pn just picked. So whenever I have this, I can generate the entire line, and for the projective space, that's it. I mean, here it's obviously more complicated because what I have here, so and I'm not for enough. Right, the first step, all these points here, I get for free, but I'm not done yet because I'm starting 2. So I have only generated a line. Now it turns out, I can pursue the game because here I have now a vertical. I can also generate this line. Points which belong to generate by this rule this line, and then I have 2 consecutive lines that I can generate this everything here. And how for P1 times P1, that is relatively straightforward. That the more complicated geometries, and also for the splitting case already, that is less tricky. In general, and I will close by this, for the argument, which is in the splitting case, due to alpha myself, and in the cotangent case, alpha Bogenegger myself. In this case, I need to phrase it differently. So any maximal exacting sequences arise from a trivial test, by delexing. So there is actually a small that is the composition of the so that is actually also which is considered in and that is the correspondence. Imagine I have a sequence of line bundles, and I just and take the class of the canonical bundle minus L in S. So this is an operation helix. Then it's followed by lexicographical reordering. And this gives this composition gives us the helix operator. Applying the helix operator a finite number of times to an arbitrary maximum of the sequence gives us one of the trillion types. And by this kind of argument, we can actually show that this operator is preserving fullness, or we can apply to the general theory which tells us that actually the helix operator is just a composition of so-called mutations, and therefore it preserves fullness. So either you teach the general theory or you do some rhetorics, but at the end of the day, it gives us that every mess arises from a test, and therefore mass implies.